extra high. Okay, Intro to Regression 101A. So we spent Monday and Wednesday reviewing confidence intervals, hypothesis testing. I hope we're all good with those concepts covered. There was, I just wanted to cover some questions that students had. There was a question about, the sampling distribution of the standard deviation, because I said only the mean follows the normal distribution, okay? And so what about the sampling distribution of the standard deviation? Well, that is actually very complicated. You can click this link, and it's like more complicated than you really wanted to know. But if you do know that the population is known to be normal with a population standard deviation sigma, so if these are known, then the sampling distribution of the sample variance times this factor comes from the chi-square distribution with n-1 degrees of freedom. So the variance, the sample variance, s squared times this factor will come from the chi-square distribution. So I think a student had that question. So just to address that, here we go. I know some of you guys had questions regarding the homework, and so I want to just address a few things that you'll encounter in the homework that I'm hoping points you in the right direction. So when you enrolled in this class, you were supposed to, someone was supposed to check and say like, hey, do you have knowledge of R? And you were supposed to be like, yes, I do, or no, I don't, so I won't take this class. But I know some of you are here without much knowledge of R, and so you're going to have to work a little extra hard because, based on the survey, I'd say about 80% of you do have knowledge of R, and so the 20% of you who don't have some catching up to do. I can't slow down the entire course on your account. So I have provided resources in CCLE under helpful resources, and again, you can access these. I'm in the browser right here. So as long as you're on the network, you should be able to view these books from O'Reilly for free, okay? And they're very useful. And so the one I recommend for just those who have very little exposure to R would be 25 recipes for getting started with R, and that will just kind of give you some basic things. And then the other things that I highly recommend are the two cookbooks here, okay? R in a nutshell is very good, but it's pretty in-depth, and you probably don't have time to work through this whole thing. But the graphics cookbook is great if you're just trying to make a graph, and you're like, how do I do this? Okay, the graphics cookbook uses ggplot2, which is an excellent package. You're gonna have to install that. Install that package is ggplot2. And I use this thing all the time because I don't have all these graph recipes memorized. So a lot of times I just look at this and say, oh yeah, this is how you do it, and then you modify it accordingly. Our cookbook also very similar in that how do I do this thing that I want to do? There's a nice little index or table of contents, and you just say, oh, I want to subset this thing, or whatever it is, okay? There's lots of stuff, and you just kind of find the thing that you want to do, and it'll give you instructions on how to do it. So those of you who are getting started with R are a little bit shaky. I think these books from O'Reilly are excellent. And as long as you're on the UCLA network, so if you're on campus and you connect, it'll be free. If you're not on campus, if you live off campus, then just VPN in, right? You guys all have the UCLA VPN. So just Google UCLA VPN, and then you'll find the instructions on that. Okay, but I just wanted to look up a couple things. So subsetting a data frame with rows. So one thing is like remove all the electric cars. So you want fuel type to be anything other than electricity. All right, that's supposed to be a capital D. So if you do vehicles $fuel type not equal to electricity, that's going to create a vector of true-false values corresponding to which cars are electric and which cars are not. Okay, if they're electric, not equal to electricity will be false, and if they're not electric, not equal will be true. So then we can subset the vehicle's data set by putting this true-false vector to specify which rows I want. And so it's important that we keep this comma here, because that's going to specify I want these rows. Okay. There's also a couple other functions that will do this. Subset vehicles where fuel type doesn't equal electricity. And then if you have dplyr, the filter function does the same thing. Okay. A lot of the code that I write uses the function package dplyr, and I'll try to do a quick tutorial on dplyr in some days in the future when it kind of lines up with the other class, and it'll probably be an extended one for two courses, for the two classes combined. So, you know, when I post solutions to the homework and things like that, you will see things in dplyr, and maybe it won't make a whole lot of sense in the beginning, but I think it's a great tool. So if you want to select the columns, you can just use $sign notation with the name of the column that you want. Okay, so if you just want the combined fuel efficiency, you just do $sign combined fuel efficiency, and you can ask the mean of it, or if there's missing values, you say ignore the missing values, etc., etc. Okay, so I'm hoping this at least gets you pointed in the right direction, especially for those of you who are really new to R and you know, are a little intimidated by its features. You don't have to be. But I do want you to just. You're gonna have to put in a little extra effort to get caught up to speed to those who at least have some basic command of the language. Okay. It's like I need you guys at like Spanish 2 level. Okay. So if you pretend R is learning a foreign language, I need you at like second year foreign language. So you don't have to be fluent or anything like that, but just a few bit things. Okay, and then the last part in your homework is making graphs for your statistical questions. So this part's a little bit trickier, and it's hard for me to offer direct guidance here just because it's very open-ended in nature. Okay, so again, I highly recommend checking out the R Graphics Cookbook, and the prompt asks you to at least involve 2 variables, and so effectively you're trying to see if there's probably some kind of relationship between variables. Some of the variables, especially if you pick a categorical variable, there's going to be a ton of categories. So for example, if you look at the variable fuel type, there's 14 fuel types of fuel that cars can use, and I didn't even know that this was possible because I always just thought it was like unleaded or diesel. You know, but they're including things like gasoline or propane, and 8 vehicles can accept gasoline or propane as fuel types. So I would say filter these out. Okay, so reduce your data frame, okay, using the subset functions that you know, and get rid of the ones that belong to kind of these highly marginal categories, because they're going to clutter any graphs that you produce, right? You don't want to create 14 box plots, probably 5 or 6 of them, okay? Because it's like just too much extra junk that detracts from the main big picture that you're trying to get. Okay, so are there any questions? Anybody struggling with the homework or anything like that? Yes, question. It's not, okay? So the vehicle's data set, and this is an important distinction, okay? It's not a random sample of cars on the street, okay? It could be considered a population of all vehicle models, okay? But for example, I mean, we know there are a lot more Honda Civics than there are Lamborghinis on the road, okay? But each one will have a single row in the vehicle's data set, okay? So it's kind of a spectrum across vehicles that are available. And so we're asking questions like, is fuel type related to fuel efficiency, or whatever it might be, other variables that you're looking at across vehicle models, but not vehicles on the street. Does that distinction kind of make sense? So it's kind of like we could create a data set of the 50 states, right? There's 50 states in the United States, and in that data set, each state would be equally represented. But would that be representative of the country? No, because California is way bigger than Wyoming, and but we might be able to still make some broad conclusions about, if we looked at the population of Wyoming and we looked at, is there a relationship between exercise and cardiac problems and stuff like that, we might be able to see some relationships across all 50 states, and we'd still be able to see like, oh, in Mississippi they have this issue going on, and in Colorado this is different, and things like that. But it would be incorrect to then average the 50 states and say this is what America is like, because that's not the case. Any other questions? Okay, let's see. So let's talk about regression. We're going to look at simple linear regression, and simple means not complex. It doesn't necessarily mean easy, although simple linear regression is probably the quote-unquote easiest form of regression. But there are a lot of important concepts that we've got to cover in simple linear regression. So we're going to just start off with easy models and talk about important concepts of regression, and then once you have that down, then you can generalize to more advanced forms. Okay? So the procedure in simple linear regression is, number one, evaluate graphics to make sure it's appropriate to use a linear model. That's step number one. Okay? Once you do that and it is appropriate, then you go ahead and fit the linear model. Then you evaluate the fit of the model, make adjustments if necessary, and evaluate and adjust as needed, okay, until you're satisfied with the model that you get. Okay, and then finally, once you're satisfied with the model that you have, then you go ahead, interpret the results, and or make predictions with the model. Okay. I think a lot of times we just think, okay, fit the linear model, now interpret the results. But we should make sure it's appropriate, and then we should always be evaluating and making sure it kind of makes sense to use this model. Okay, so looking at a scatter plot to make sure that it's a linear model is appropriate. So things that we want to look for, we want to describe the trend. Okay, how did the typical values of y change with x? Okay, does y generally increase as x increases? Does y generally decrease as x increases, or does it do neither of those things? Is the shape linear or exponential or some other shape? Okay, those are things that you want to look for in trend. Then you want to look at the strength. How much variability is there in y for each value of x? Okay, so that's looking at the strength of the relationship. And then are there any unusual points? Okay, and I want to compare this process of examining a scatter plot with how you would describe a histogram. Okay, and so in your intro stats class, you should have learned how to describe a histogram by discussing the center, the spread, the shape, and the unusual points, which is very similar, right? With the center, you're looking at a typical value instead of the typical trend. The spread, how much variability is there? The shape, is it symmetric or skewed? Okay, so with a histogram, you're looking at center, spread, shape, unusual points. Scatter plot, you're looking at the trend and strength, but also the shape and unusual points. Okay, so just for an intro data set, we're going to take a look at NHANES. NHANES is the National Health and Nutrition Examination Survey. They survey about 5,000 people every year. It's not perfectly representative of the United States, okay, and they they purposefully interview certain minorities, groups at a higher proportion, and this is all explained on the NHANES website. So the real data set is gigantic, okay? But you can get kind of a sample of this data set with the package NHANES in R, so you don't even have to bother about drawing, downloading stuff, okay? Just do it. Well, you're gonna have to download the package NHANES, but it's all into built in R itself. Makes it nice and easy. Okay, so here I'm going to look in this data set and see if there's a trend. Is there a relationship between the height of someone and the weight of someone? Okay, so these plots have been created in ggplot, and I'll post the R Markdown code so you can see exactly what commands I've written to produce this plot. Okay. Okay, so what do we see? Do we see a trend between height and weight?
Yes.
Okay, and the general trend is what? People who have higher height generally tend to weigh more, okay? And it seems very true down here. What's going on down here? The height is measured in centimeters and weight's measured in kilos. So what's going on down here? These are little kids, okay? These are kids growing up. So they're getting taller, they're getting heavier, okay? So that's a very strong relationship when you're a kid, okay? And then when you're a grown up, then height becomes less of a predictor for weight, okay? Because you got short people who are light, short people who are heavy, tall people who are light, tall people who are heavy, things like that. But overall, even as grown-ups, we still see a trend where taller people generally weigh more. So I just did a filter and I said, let me look at people under age 18, and we see a pretty strong, I would say, linear trend overall. And then for those, for those over 18, you know, at least this cloud seems like there is some kind of positive trend, but there is a lot of scatter, right? You know, this person weighs, 200, you know, I don't know, 25 kilograms. Okay, that's slightly worrisome, but but there are people. Okay, so you know, and this person is 200 centimeters tall, which is very tall. So that's 2 meters tall. All right, so let's take a look. We can describe the trend, the strength and direction of a linear relationship with the correlation coefficient R, okay? So the correlation coefficient R is just like any other statistic. You've got the standard deviation, which puts a number, quantifies the amount of spread. Okay, so we've got spread, this concept of how much variability there is. Standard deviation quantifies it. Correlation coefficient, we've got the concepts of strength and direction, and R quantifies it. So this is how we calculate R, okay? So recall that a z-score measures how many standard deviations an observation is from the mean. So we take, for x, you'd take x, the observation, subtract off the mean of x, and divide by the standard deviation of x, and you get the z-score. So the Pearson correlation coefficient is the sum product of those z-scores, you know, and then kind of divided by n1 minus 1 is this adjusting factor. But you take, effectively, you're taking the z-score for x and the z-score for y. So we're just saying, is x above the mean? Is y above the mean? Or is x above the mean and y below the mean? You know, how much above the mean and things like that. So we are adjusting these things, and this gives you the correlation coefficient R. Okay, so these are some facts about R. R has no units. Both variables are standardized. So if we looked at the correlation coefficient between height and weight in centimeters and kilos, it will be the exact same if we changed units from centimeters to inches, or if we changed units from pounds to kilos. Okay, it's unitless. So that's what happens. R doesn't care which variable is x or y. So if the correlation between height and weight is one value, the correlation between weight and height is the exact same thing. Okay, and R is always between -1 and 1 and 1 inclusive. These are in the interpretations of R. Okay, R is negative if the direction is negative, direction of the relationship. R is positive if the direction of the relationship is positive. R is 0 means there's no association, where R equal to 1 or negative 1 means perfect linear association. Okay, and this is important. Assuming a linear relationship, values of R that are close to 1 or minus 1 suggest high predictability. But this is very much dependent on this, the fact that there's a linear relationship. Okay, if you don't have a linear relationship, these interpretations of R no longer are valid. Okay, so we're going to calculate R by hand for one very small data set. Okay, and I promise this will be the only time we do this, because computers can calculate R, the correlation coefficient, for us very quickly and accurately. Okay, but I think there is some merit in seeing it done for a very small data set to see exactly where these things are coming from. So I'm going to rework our formula into a version that's a little bit easier. Okay, so whenever you have something inside the sum, you can factor them out if what? If they're not affected by I, right? So n minus 1, this is going to be the same for everything, so I can just factor that out. Okay, and then so now I've got zx and zy sub I, and I'm going to just turn those back into their z-score formulas, xi and x bar and all of this. Okay, and again, because the standard deviation of x and the standard deviation of y are not affected by I can also factor those out. Okay, so I've got this formula, 1 over n minus 1 s standard deviation of x, standard deviation of y, and then I just have to look at the difference between each point and the mean of its brethren, I guess, x and y. And we're going to look at the sum product across all of our points, and then we can calculate our correlation coefficient R. Okay, so we're going to look at some, I'm just making up some fake data here, and we're going to just pretend we took a random sample of 4 dwelling spaces, okay, and we're looking at the number of bedrooms and the number of closets, okay, and this is very ridiculous, but I think it illustrates what I'm trying to get at, okay. So we have a place with 1 bedroom and it had 2 closets. This place had 2 bedrooms and it had 6 closets. I don't know why. And this place had 3 bedrooms and it's got 4 closets, and this one has 4 bedrooms and 8 closets, okay? So we want to know, can we create some kind of, can we get a correlation here? Can we create a trend line, things like that, okay? All right, so let's just plot our data, and this is what it looks like. And does it look like there's some kind of linear trend? Maybe, I don't know. I have 4 data points, it's hard to really say anything meaningful, but we're just going to pretend like, oh, okay, sure. As the number of bedrooms increases, the number of closets increase, and that at least kind of makes sense in real life as well. Okay, so let's take a look at this, okay? And so for each point, we calculated the mean of x. Basically, you just take these 4 values, add them up, and divide by 4, and you do the same thing for y. So the mean of x is 2.5 and the mean of y is 5. So I'm going to do x minus the mean and get these values, and y minus the mean. I'm basically calculating these 2 things. And then let's do the product, okay? So if I do that, 1 minus 2.5 gives me negative 1.5, and I do this and I get all of these values. I do the same thing for y. I'm subtracting off the mean of 5 for each value of y. I get negative 3, 1, negative 1, and positive 3, okay? This is okay, right? I just want to make sure. Okay, and then so lastly, we're going to multiply these 2 together, and then we're going to add them up. Oops. Okay, so you multiply the negative 1.5 and the 3, and you get positive 4.5, and you multiply these, and you get negative 0.5 and negative 0.5, and then you get positive 4.5. So we've done this calculations. And then if you add up this product, you get 8. So this entire part over here, from the sum to this is equal to 8. Okay? And then, all right, so let's just throw in our values. If I calculate the standard deviation of x and the standard deviation of y, I'm going to get 1.291 and 2.582. And when you multiply this out, you get 1 over 10. And so r is 0.8. Okay, so that is the correlation coefficient between x and y when we're looking at bedrooms and closets in our simple fake data set. Okay, and so again, looking at this, we can think of this faint line right here. This represents the intersection between the mean of x, which is 2.5, and the mean of y, which is 5. Okay, and so what we see is that this data point is far above x, far above the mean of x, and far above the mean of y. Okay, and so this z-score for x is positive and the z-score for y is positive, and it's large, so it contributes a large amount to the positive direction of the correlation. Okay, this one is far below the mean of x and far below the mean of y, so its z-score for x and z-score for y will be negative and negative. So when you multiply those two together, you get a positive value also. These ones, you just have the opposite. These ones, this is above the mean in x but below the mean in y. So you have a positive z-score for x and a negative z-score for y. It's going to contribute a negative amount towards the correlation. Same thing with this point. It contributes a negative amount towards the correlation. But what we see is that because the magnitude or the distance these are from this mean here, this central point, is greater for here, these contribute greater amounts for the positive correlation than these contribute in the negative correlation. Okay, and so we can see that when we did the product of x minus x bar and y minus y bar, we're getting positive 4.5 over here by those two endpoints, and then the two middle points each contribute negative 0.5. So that's why our overall correlation is positive at 0.8. Right? Okay, what if my 4 houses or dwellings looked like this? Okay, I got one bedroom place with 8 closets for some reason. Okay, and it's like and then I've got a 4-bedroom place with only 2 closets and things like this. Okay, so what's the correlation here going to be? It's going to be 0, right? Because the positive amounts contributed by these 2 points will be canceled out by the negative amounts contributed by these 2 points. Okay, and we can do this if we if we did the sum product, just that part, we can see that positive and negative, they all cancel each other out, and you get a sum of 0. Okay, and so when you ask a computer to you throw 1,000 data points at it and you say, give me the correlation, this is effectively what it's doing. It's probably got some algorithms doing it a little bit faster than we would, but it's just saying, okay, I'm going to find the x bar and the y bar and set this as kind of this middle point, and then I want to see how much above or below each of these points are in the x and y directions, whether they contribute positively or negatively to the correlation coefficient, and it figures that out. Okay, so this is how we're getting our correlation value R. Okay, it's really important that we create a scatter plot before we look at the data, okay? Because you can just throw data at a computer, it'll spit back a correlation coefficient, and it's tempting to just take those things and then start making interpretations, okay? So maybe you're familiar with the Anscombe data set, but here we have 4 data sets. X1 is paired with Y1, X2 is paired with Y2, X3 with Y3, and X4 with Y4. And you'll notice that for the X variables, 1, 2, and 3, they all have the same values, okay? X4 is a little bit different, and we'll take a look at that. And then as we look at Y1, Y2, Y3, Y4, our eyes can't really tell anything. It's just like, okay, there's numbers over there. But we can do some summary statistics. We can say, okay, well, what's the mean of x1 through x4 and y1 through y4. And we see that the mean values for each of these things are exactly the same. We got 9 as the mean for each of these things. And then for the y's, the mean are all pretty much the same, okay? 7.5, 7.5, maybe with just a couple extra decimals here or there. But effectively, the mean of y is 7.5. We look at the standard deviation for the x variables, and we see that for the x variables, the standard deviation is exactly the same also, 3.32 effectively for all of them. And for y, the standard deviation is also about the same, 2.03 for all 4 data sets, okay? So far all of these things look about the same, okay? And we can even ask the correlation. What's the correlation between x and y? So we look at x1 and y1, we get a correlation of 0.816, 0.816, 0.816, 0.816. So we're getting the same correlation values, okay? So it might be tempting to just say, oh, okay. So because of all of these things, they're actually going to have the same fitted regression line, okay? And it might be tempting to just say, okay, well, let's just fit the regression lines and see what happens, okay? But if we look at the plots, okay, here's x1 and y1. Here it seems appropriate to fit a linear model to the data, okay? It seems overall there's a positive trend, and it seems like overall, you know, a linear fit to the data seems appropriate, okay? But let's look at the next data set. Okay, what do we see here? Okay, we see something that's clearly not linear. We see kind of this arch in the data, and it seems like what would be a more appropriate fit?
Quadratic.
Like a quadratic, right? Okay, like a parabola of some kind, and it's just because it cut off here that we're getting an overall positive trend, okay, in terms of the correlation being 0.816. But a linear model is clearly not appropriate because it doesn't fit a straight line, okay? What's going on here? Okay, we have a perfectly straight line over here, okay, so we would expect a correlation of +1, except what happened? We get one outlier that's way up here that throws everything off, okay? And so we have one data point that's messing everything up. We would want to actually investigate what this point is. Maybe it's a typo. Maybe there's a typo and that's why it's up there. Maybe there's a good reason as to why it's out there, okay? It's worth investigating rather than just saying, let's kill it, okay? And then lastly, here we're fitting x4 and y4. We only gathered data where x was equal to 8. Okay, we only gathered data where x was equal to 8. So it would be incredibly a bad idea to try to create some kind of trend between x and y when you've only looked at one value of x, right? You're trying to see how does y vary when x varies, but you didn't get any measurements for any other values of x except one data point out here at 19. Okay, this is the only data point you got where x was not equal to 8, and you're trying to base your entire judgment of the relationship between x and y on this single data point. Okay, it would be as if you lived in an isolated country or something, and so everybody you knew was similar to you, okay, so your same ethnicity and same viewpoints, and then you met one foreigner, and this one foreigner was a huge jerk, and then you're going to say, oh well, every single foreigner out there in the world are jerks and terrible people, okay? It would be you're seeing variation in your own neighborhood or whatever, and then you encounter one person outside of that, and you're trying to make a judgment based on that, okay? And that's not a good idea, okay? And even if you had like just 2 data points or something, that's a little bit better. But you see this is a ridiculous example, but a lot of times you see people trying to make strong conclusions based on very limited amounts of data, okay? All right, so what does this mean? Okay, The correlation coefficient by itself won't tell you what the scatter plot will look like. However, if you do know that the trend is linear because you looked at a scatter plot, then the correlation coefficient does tell you about the strength of the association. So that's, it is very important that we create graphs. Okay. Let's talk about the best fit line. So we're going to go back to our silly bedroom and closet data. And let's say we wanted to fit a model that we can use to predict the number of closets in a dwelling based on the number of bedrooms. Okay. So how do we know what line is going to be the line of best fit? Okay. And so I think if I were to ask you to create a line of best fit, a lot of you would say, hey, this is a pretty decent line. And I apologize for the scaling here being so off. I'm trying to, I was trying to get X and Y to be on about the same scale of squares here. So, anyway, so this is the place with 1 bedroom and 2 closets and 4 bedrooms and 8 closets. And you might create this trend line and say, that seems pretty reasonable, okay? And then others of you might try to approximate it with something like this, okay? And so here are 2 trend lines. Which one is the better fit? That's the question. We want the best fit line, okay? So how are we going to evaluate what line is a good fit, what line is better than another fit, what line's not a good fit, okay? So we have 2 potential models that seem reasonable, okay? And so one, if we create the equations for these, we have f of x, or y, is equal to 2x, and the other one is 1 plus 1.6x, okay? So 1.6x is the blue line, and 2x is the red line. Do you guys have a gut feeling as to which one's better, or what you would draw? Red, blue? Okay, well, let's see. All right, so we have to introduce the concept of residuals, which is no matter how good our model is, it's not going to predict all points perfectly, okay? And the difference between a prediction and the actual value, that's known as the residual. So the residual is equal to the actual value minus the predicted value for a particular value of x, okay? So if x equals this and you're predicting, 4 bedrooms and it actually, or 4 closets and you're predicting, and it's actually 6 closets, then you have a residual of 2, okay? So the residual E is y minus y hat, or visually this is the vertical distance from the point to the prediction line. Okay, so for the red line goes through these 2 points, so there is no residual here, and then this is the residual for the other 2 rooms. So this is, we predicted when x equals 2, we predicted that y would equal 4, and in reality that dwelling had 6 closets. When x equals 3, we predicted that y would equal 6, and that dwelling actually had 4 closets. So these are the residuals here, okay? And over here, this was a pain in the butt to graph, by the way. With the blue line, we have these residuals, okay? So it's the vertical distance between the actual data point and our prediction for when x takes on that value. Okay? And again, but the code for these graphs are in the R Markdown files if you want to look at them. Okay, so the best fit line is the least squares line. Okay, and what we're going to do is we're going to square the residuals and we're going to add them up. Okay, and the line that produces the least amount of residuals is going to be deemed the best fit line. Okay, so this is what we're going to do. So I've taken this residual and I've squared it. Okay, and these are supposed to look like squares, and I'm hoping they are. And so we're going to take this total area of this grade square area. Okay. This is the blue line, and this is the total area here. Okay, so which one has more area total? Red, blue, red. Who do you think? Which one has more sum of squares residuals? They look very similar, right? Okay, so we have to do some math here, okay? Oh, I should have put in the table, but I didn't. Okay, so if we looked at each data point, so if this is for the red line, okay, the two endpoints had no residual, so that would be 0 squared. The 2 points in the middle had a residual of 2. We predicted 4 and it got 6 and things like that. So we add them up, we get a total sum of squares of 8, okay? You can go through the math for the other one, okay? If we plug in 1 plus 1.6x, and you calculate the residuals for each one, you get 0.6 squared, 1.8 squared, etc., and it adds up to 7.2. So they're very close. They're only off by about 10% of each other. But so if you look, the blue line has ever so slightly less sum of squares, okay? So model 2, the blue line, is better according to our evaluation criteria. And so our best fit line is y hat equal to 1 plus 1.6x. Okay, is that good, how we pick out the best fit line? Okay, and so these are the formulas if we want to get into this. Okay, so the linear mean function of our best fit line is going to be b0 plus b1x, okay? And the least squares criteria is written as the difference between each individual point and our prediction. We take that difference and we square it and we add them all up. Okay, and so this is how we and we're trying to minimize this sum by adjusting b0 and b1. Okay, so how do we pick b0 and b1? All right, so I'm going to skip this part. I'm assuming it gets covered in 100B in the mathematical statistics, all of this stuff. So with some calculus and algebra, right, you set your derivatives equal to 0 to find the minimum point and things like that. Anyway, it turns out that the slope of the best fit line actually has this nice form of correlation r times the standard deviation of y over the standard deviation of x, okay? And then the intercept of the best fit line goes through y bar and x bar with this. This is like point slope form, right? Oh, and this is now slope intercept form, but you could have gotten it that way. And so our best fit line y hat is you just combine these two together, okay, to create this. And so again, I'm skipping the proof because we leave that to 100B. For all of the proofs behind all of these things that I'm showing you, okay? And you just have to say, oh, okay, that's nice that somebody else proved it. Because that's what we do in life, right? Like, we don't have to prove that the car works. It does. Okay, so now how do we do this with R? Well, it's very easy. I'm going to create this data frame called dwelling or dwell. And that's 1 through 4, and the bedrooms or closets will be 2, 6, 4, 8. I'm going to just create an object called my model, and I'm going to use the linear model function lm and say y as predicted by x using data dwell. Give me my model. Boom, done. Intercept 1, slope 1.6. Okay, or the coefficient associated with x, which is the slope of x, is 1.6, and the intercept is 1.0. Okay, and then if you ask for the summary of my model, then it tells you all of those residuals that you had, which you square and say, oh, that's going to be the sum of squares residuals, and it gives you all of these things. We'll talk about the p-values associated with these things, whether they're good or not, and we can talk about all of these other things. But it's very simple to do regression in R. There's at least a very simple model to begin with. At least fitting the model is easy, but right, we have all those other steps of evaluating the model, making adjustments, and there we go. Okay. If you want to create a plot, you can do plot y as relates to x, and it puts those dots up there. This is the built-in plot functions, and then you just say AB line my model, and when you feed my model into AB line then knows hey, you're giving me a linear model. I'm going to pick out the, where'd it go? Intercept and slope. I'm going to pick these out and graph the line, okay? Which is really nice. You don't have to generate an index of x's and y's to do all of this, okay? And then you can do the same thing with ggplot. You just say, okay, use ggplot, use the dwelling data. X is x and y is y, or x is, you would, if you named them other than this, you would say x is bedrooms and y is closets. And then you say, well, I want to create points, and then I'm going to create the what's called the smooth line in ggplot, and we're going to fit it using a linear model. A lot of times it defaults to including confidence bands, which we'll talk about in the future, but for now we turn them off and we have this. Okay, oh, perfect. So, so we end there, and I hope the homework assignment is going okay. I do have office hours on Monday from 5 to 6, but that's cutting it close. So don't come to office hours on Monday saying, I don't know how to do the homework. You better have done as much as you can, and then maybe you have a few questions left, okay?
Are you going to send an email about the time that we're going to cover
Do
how to
dplyr? Yeah, I'm still trying to work out the schedules between the two classes to figure out when it would be best.